Okay, Assalamualaikum and a very good morning. Okay, next we are going to discuss another important parameters in antenna in measuring the antenna performance, which is the polarization. So as we know that the electromagnetic wave consists of two vectors, which are electric field vector and magnetic field vector that in orthogonal or in perpendicular to each other. Right, so polarization basically defines the behavior of the electric field component as it propagates in time. Okay, so in this case, the electric field component travels or propagate in vertical orientation. Okay, if the E field is travels or propagate in horizontal linear, so we may see that the E field will oscillate linearly in horizontal direction, while when the E field vector orientate vertically across the propagation direction, so it is vertical in vertical linear polarization. So basically the polarization is the orientation of electric field as a function of time. Okay, the slide summarizes some of the illustration on electric field vector rotation or polarization. For example, this is your antenna. So we can see that the E field radiates or propagate horizontally across the propagation direction. And this is for vertical polarized, in which the E field travels in vertical orientation, and dual polarized when the antenna radiates the fields which have both the vertical and horizontal polarization. And this is the cross polarization, in which the signal is slanted or is propagate in plane that is 45 degree if compared to the horizontal or the vertical plane. And this one is the secular polarized and also secular polarized in left hand or right hand direction. Okay, to achieve best results, the transmitter and the receiver must have same polarization. Okay, so the polarization must be matched in both the transmission end and the receiving end. So for example, the blue one indicates the signal propagate from the transmitter in horizontal polarization. So at the receiving end, represented by the yellow lines, so the antenna is oriented in the same polarization direction. What happens if at the receiving end, the polarization plane is angled if compared to the original transmitting the signal from the transmitting end? So the signal received will be distorted, or the level of the received signal will be reduced. Okay, when an antenna having both the vertical and horizontal polarization, but in practical, the vertical and the horizontal polarization is not perfect, or it is not completely orthogonal. Okay, so therefore for dual polarized antenna, there's a parameter called cross polarization. cross polarization, okay, in which it determines the level, or it separates the vertical and horizontal polarization during the transmission. So the higher, okay, the parameter is called cross polarization isolation. Okay, the higher the isolation is, the better. Okay, because the isolation will basically determines how effective the vertical and the horizontal polarization signal will be separated from each other. Okay, types of polarization. There are three main types of polarization, which are the linear polarization, circular, and elliptical. So for linear polarization, the fields oscillate in one direction, okay, at a fixed time over distance. Okay, so the linear polarization may be vertical polarization, horizontal, or any angle in between. So any angle in between is something like the slanted. So we have this one. So this is the slanted. Okay, so this is categorized as linear polarization. So in linear polarization, it has one component, or the signal oscillates in one direction, or if it has two components, orthogonal component, the magnitude must be the same and both components must be in phase. Alright, so for circular polarization, okay, it has two components, vertical and horizontal, which are orthogonal to each other. Okay, that's 90-degree separation between them, and it can be categorized as left-handed or right-handed. So this is when it oscillates in clockwise, so it is right-handed, and the other way around is left-handed. Right, for circular polarization, we don't have to worry about the angle, okay, between the transmitter and the receiver, because the signal oscillates in all directions. Okay, for elliptical, it's more or less the same as circular, but the magnitude or the voltage of one of the component, for example the vertical component, okay, so the magnitude of the vertical component is higher than the horizontal component. Okay, so it developed the elliptical shape. Right, so the ratio between the two voltage amplitude between the vertical and horizontal is called axial ratio. Right, so when the axial ratio equal to 1, so meaning that the polarization is actually the circular polarization, when it has the ratio the same magnitude for both the vertical and horizontal. Okay, this slide shows a sample of input signals, different orientation of the transmit antenna and also the receive antenna, and look at how the receive signal looks like when the polarization is similar or different to the between the transmitter and the receiver. Okay, for example, the first one, we have the input signal, and then the transmit signal is basically in horizontal direction, and the polarization also in H direction, horizontal direction, and the receive antenna having the same polarization direction. So the signal, the received signal is actually similar to the input signal, in which most of the system from the output of the system, we expect to have similar output as compared to the input. Okay, if you look at the second signal, the same input signal, okay, the antenna oriented vertically or in vertical polarization, so the signal transmitted in vertically. However, at the receiver, the antenna is oriented horizontally, so having horizontal polarization. So therefore, due to the different polarization at the transmitter and the receiver, so the received signal basically having lesser or distorted characteristic if compared to the input signal. Okay, so same goes to the third one, when the transmitter and the receiver having different polarization. So for the received signal having level of signal that reduce if compared to the input signal. Okay, so we have seen illustration of polarization and also definitions of different types of polarization. So now we are going to analyze the polarization mathematically. Okay, consider a plane wave traveling in negative z direction given by this equation, in which it consists of two components, x and y components. And the x component is given as ex naught cos omega t plus kx plus phi x, and the other one for the y component. Okay, for linear polarization, the time phase difference between the two components, between the y and x components, must fulfill this equation. Delta phi, the time phase difference, equal to phi y minus phi x equal to n pi. Okay, meaning that when the two components must be in phase or out of phase, okay, 0 or 180 degree. So for secular polarization, to achieve secular polarization, it can be achieved only when magnitude of both components, the x and y components, are the same. The magnitude must be the same length, and the time phase difference is odd multiple of pi over 2. Okay, odd multiple of 90 degree. Okay, for secular polarization, the magnitude for both components are the same, and the time phase difference must be the odd multiples of pi over 2 or 90 degree. Okay, so either it is in clockwise or anti-clockwise. So we can say that the components is in orthogonal to each other. Okay, for elliptical polarization, can only be achieved when the time phase difference between the two components is odd multiples of 90 degree, so as similar as secular polarization. However, the magnitude for both components are not the same in elliptical polarization, or when the time phase difference between the two components not equal to multiples of pi over 2, irrespective of their magnitudes. And both conditions can be represented by the equation shown on the right hand side. Okay, so in this case, the first case, it is more or less similar as secular polarization, but the magnitude is not the same. And in the second one, when the phase is not equal to a multiple of pi over 2. Right, the ratio of the major axis, or the main, the longer beam to the minor axis is referred to as axial ratio AR, and it is given as the ratio between the major axis or the longest beam to the minor axis. So in this case, represented by OA to OB. And the tilt of the ellipse related to y-axis, so this is y-axis, so the tilt is represented by tau given by this equation. Okay, so OA and OB is the length of the major and the minor axis, can be calculated by using this equation. Okay, this slide summarizes the characteristic for three different polarization: circular, linear, and also elliptical polarization, as we have discussed in the earlier slides. Okay, next is the polarization loss factor. We have seen this figure earlier. Okay, to achieve best performance, the transmitting antenna should be in the same polarization as the receiving antenna. However, when the receiving antenna is angled or not in the same polarization as the transmitting antenna, so a mismatch happened. Okay, so the PLF or polarization loss factor happen when the polarization of the receiving antenna is not similar as the polarization of the incoming wave. Okay, incoming wave, this is incoming wave or incident wave. Okay, so when a mismatch happen, the power from the incident wave cannot be extracted at maximum level. So there's maybe distortion in the receiving signal. Okay, in terms of the mathematical representation, so polarization loss factor or PLF can be calculated by multiplying the two unit vector. So the incoming wave, the electric field of the incoming wave is represented as EI. The electric field of I incident wave equal to the unit vector of the wave, the incident wave multiplied by the electric field of the incident wave. Okay, so rho omega or rho W is the unit vector. Okay, what is unit vector? So unit vector is the vector divided by the magnitude of the vector. Alright, okay, you need to revise this from the EMT course. Alright, so for the receiving antenna, the electric field of the receiving antenna is given by EA equal to the unit vector of the antenna multiplied by the electric field of the antenna. Okay, so the PLF is equal to the multiplication dot product of unit vector W with unit vector A antenna squared, and it is equal to cos psi p to the power of 2. Right, so psi is actually the angle between the rho omega, the incident wave unit vector, and the antenna unit vector. Okay, and this figure basically shows the alignment between the incident wave vector, unit vector, to the unit vector of the antenna. Okay, these slides illustrate the power loss factor for different types of antennas. Okay, for example, power loss factor for aperture antenna, PLF equal to 1 when the transmitter and the receiver is aligned for aperture antenna. Okay, so this is the aperture antenna. So the transmitter having the same polarization as the receiver. So the PLF equal to 1. So when there's a rotation for the receiving antenna and the incident wave, so the PLF is equal to rho omega dot rho A squared, in which you can see that there's rotation, okay, in between the incident wave and also the antenna. And PLF equal to 0 when the polarization of both components are orthogonal to each other. Alright, for linear wire antennas, so when it is aligned, so again PLF equal to 1 when both the transmitter and the receiver is aligned. And when there's angle or rotation, so the PLF is equal to the dot product of the incident wave and also the antenna unit vector, and it is equal to 0 when both components are orthogonal to each other. Okay, let's look at one example. The electric field of a linearly polarized electromagnetic wave given by EI is incident. Okay, so this represents the incident wave upon a linearly polarized antenna whose electric field polarization EA. So this is polarized antenna, so the electric field is given by EA. So given the EI and EA as the following equation, so find the polarization loss factor PLF. Alright, so in order to solve this, first I would recommend you to write down the general equation for PLF. So from previous slide, we know that PLF is equal to the dot product of unit vector W, the incident wave dot product of rho A, the antenna unit vector of antenna. It is also equal to the magnitude of cos psi p squared. Okay, next compare the general equation of the EI and EA with the given equation. So we know from general equation of EI is equal to the rho wave, so incident wave multiply with EI. So compare with the one you have. So EI equal to EX E naught, and the other one for the antenna, so EA general equation rho A EA multiply. So compare with the given equation of EA. So in this case, EA equal to the vector represented by EX plus AY E. Okay. So now we know that for a unit vector of a wave, rho omega is equal to AX. Unit vector of rho omega is equal to unit vector of AX. So for the antenna, so rho A is equal to, when it is a unit vector, it is actually the vector, so AX, when there's more than one vector involved, so AX plus AY divided by the magnitude of the vector. So in this case, it is equal to AX plus AY divided by Z2. Okay, so next, the power loss factor is equal to the magnitude of rho omega dot product rho A squared So it is equal to rho omega is equal to AX dot rho A equal to 1 over Z2 AX plus AY squared. So this is equal to 1 over 2. So power loss factor in dB. So in dB, so PLF equal to 10 log 10 of PLF. It is equal to 10 log 10 of 1 over 2, which is equal to minus 3 dB. So the power loss factor for this particular condition is minus 3 dB. With that, thank you.